recording.
Okay. So we'll go through these kind of quickly because you've done all these types of graphs before. So I think it'll be just a quick review. We'll look at it both ways. If you wanted to do it graphically, it might be a little bit difficult, like you guys said, if the y-intercept is off the graph. But it says write the equation of the line that goes through the point 5, 2. So it has to include 1, 2, 3, 4, 5, 5, 2. So we want the line that has to include that point, has to have a slope of -3. So we can work it both ways. Down 3 over 1, down 3 over 1. Because essentially, what piece of information do we need to know yet? We need to know what the y-intercept is, because then we can write the slope-intercept equation. Okay? So if we work our way back, up 3, back 1, up 3, whoops, up 3, back 1. So you could kind of, like I said, you'll just have to, you could kind of work it. This will be a little harder to do graphically because it'll be off the graph. But you could figure that out. You would just figure, okay, right now we're at 8. We're going to go 9 more up. So it's going to cross at 17, yes. So that would tell you, so if we just kind of just estimate here, so that's going to cross at 17. So our equation would be, our slope was -3, our y-intercept was +17, okay? Let's take a look at it algebraically. So we take our equation, what we're just going to do, since I don't know what my y-intercept is, I'm just going to put b. And then how would we be able to algebraically figure out? Say that again?
Minus the 2 on one side of the equal sign.
We can just,
Yeah. Slope x minus and then distribute.
okay, yeah, that's a different, just a different form. Well, usually what I like to do is I'll just substitute in. This is one of the, they gave us, we were given 5, 2. Since that's a point on the line, I'll just substitute that in there. So y is 2, x is 5, and then, whoops. And then solve that for b. So either, if you, yeah, like I said, either method, if you'd like to use that little bit different one that they have in the book, that's fine too. So here you get your y-intercept of 17, okay? So you could do it either way. So we had our slope of -3 and your y-intercept of 17, okay? Let's take a look at our next example. I'll do 2 of them here. And just move this over a little bit, okay? Our second example is write the equation of the line that goes through the point 1, 5. Let me do it in red this time. So 1, 2, 3, 4, 5. We want it to go through that point parallel to the line whose equation is y equals -3x plus 2. So in other words, we graph that. Down 3 over 1. Okay. We want it to go through this point. We want it to be parallel to this one. If it's going to be parallel, same slope. Very good. So we know it's got to have the same slope. And this is a nice one to work out graphically, because what's the y-intercept going to be for the other line? We do our slope, go up 3 and back 1. Yes. Right. So we wanted it. Our slope is still the same as that one, but now our y-intercept is going to be 8 instead. Okay. If you want to do it algebraically, it'll be the same as the other one. I would just substitute in that for x and y. In other words, I know I'm going to have, let me just put this. I know I want the same slope as this one because I want it to be parallel. So -3, and then I would put in, like I said, my x and y. My y is 5, my x is 1. Okay, that'd be another way to figure out your y-intercept. Okay, let's take a look at this example down here. They're pretty much, you'll work them out real similar. It's just that now, if you get a slope of -3, or you can think of it as -3/1, if we want to do a line perpendicular to that, now our slope is going to be +1/3. So you would take a slope of +1/3, and then you would substitute these 2 points, the point in there 9, 4, because that's the point that we want. So you would say 4 is my y, so 4 equals 1/3 times 9 plus b. So if we graph this one, we got this was same as the other one. Here's our first line. I wanted the other one to go through 9, 4, and I wanted it to be perpendicular to that. What's 1/3 of 9? 3. So I've got 4 equals 3 plus b. So that tells me if I keep this line going at a slope of +1/3, it's going to have a y-intercept of, well, over here. So you have a y-intercept of 1. So what's the equation I want then that I'm looking for? Okay. Yeah, Brad. I'm just using still the slope-intercept equation. Yeah. Okay. I'm going a little fast, but if you want to review any of that, it'll be online tonight. Okay. If you just have 2 points, so -2, -1, and 3, 4, I want to get the equation for those. Sure. Can you, I know it's maybe a little hard to see, can we count out what the slope would be? Is it 1? Because it's up 1, 2, 3, 4, 5, and over 1, 2, 3, 4, 5. Okay. So you're right. Slope of 1. And then, so I'll just say x, and then my y-intercept is going to be 1. So keep, yep. That's a pretty easy one. If we were going to do that algebraically without using a graph, how would you do that? You would just use your equation to find the slope. So -1 minus 4, -2 minus 3, So that tells me my slope is 1. And then when you have your slope then, how could you figure out, so again, we're trying to get this equation. I know my slope is 1. How would you figure out what your y-intercept would be without having a graph? What's that? Sure, which one? Sure, and actually it doesn't matter which one. They're both points on the line, so it doesn't matter which one you use. So maybe if you want to keep it positive, you could use 3 and 4 too. So you would put in 4 for y. Your slope we figured out is 1. You put in 3 for x, and then you just solve that for b, which if we subtract off 3, you're going to get your y-intercept as 1. So that's how you do it algebraically. Okay. Now, this will probably be a little new. There's still linear functions, but it might be a little new terminology. Okay? Got 3 different examples. We'll just say A, B, and C. Could anybody think, so in other words, you noticed, say you're in the store, and you noticed here are 4 different prices. It's the same item. Okay? And you noticed if you buy 8 ounces of it, that's the price. 11 ounces is that, and so forth. We want to know if it's what we call direct variation. It's basically, I'm asking if it's consistent. Can anybody think of a way you could check to see if their pricing is consistent? Brad?
Take the price divided by how many ounces to get it to 1 ounce.
Sure. Yes. Very good. Get the price per ounce. If they all have the same price for 1 ounce, then it would be direct variation. It's consistent. So take your calculator. Grab mine here. Oops. Let's set mine. Okay. Well. Thought I had mine in there, but maybe not. Divide those out and see what you get. So we got 9.6 divided by 8. That's 1.2. 14.3 divided by 11. So right away we know it's not. Okay? So we would say no, it's not direct variation because it's got to be consistent the whole way through. Okay? So that product doesn't have consistent pricing for different weights. It should be the same price per ounce no matter how much you get. Okay? A different example. We've got, it says years since 2002. Say this is a city, this is an area that has really sprouted up. It's really grown. Okay? And these are the different populations we've had since. In other words, this would represent the year 2010, this year. Okay? What do you think? When you divide those, 16,000.
Yeah, they're all.
Okay. So we would say yes, it's direct variation. Now, you guys, we got to go a little further on this one. We want to figure out what we call the constant of variation. So in other words, what I want you to write down, your equation for direct variation, this is the lowercase k. It's pretty much just, we've done linear equations. If I were to write out something like this, what's the y-intercept of that? 0, and the slope is 5. This is basically the form for direct variation. You're going to have a y-intercept of 0, and then k is your slope. So let's write this down first, though. So k is what we call our okay. And I'm running out of room here a little bit, so I'll write it over here. Now, if you were to sometimes you'll call it the constant of proportionality. If you were to solve this for k, this formula for direct variation, how would you do that if you were to solve that for k? How would you get k by itself? Divide by x, good. So if you divide both of these by x, this is what we were doing. That's what I wanted to show you. You've got k equals y divided by x. That's what we were doing. We were taking y divided by x. So that's another form of the formula for direct variation. It's kind of like rate times time equals distance, or you could also do that, say like time equals distance divided by rate. It's just a different form of the same thing. So in this one, you guys, we were dividing those. We took x divided by, or y divided by x. We got 16,000. So if I asked you for this city, if I asked you to write the equation for the direct variation, you would say y equals 16,000x. 16,000 is the k, or the constant of proportionality, the constant of variation. Okay. Let's take a look at this one. We've got these, just to give you an idea of what it's talking about, if I just make a quick little sketch here of the waves. What they're talking about is the length of the wave from crest to crest. So that's here to here. So basically the top of the curl of the wave. And then this is the height of the wave. So in other words, basically how tall it is. Okay, so we want to see if there's a consistent relationship here. So 4 divided by 28, that gives us, it would be like 1/7. It's 0.142. If we take 3.6 divided by 25.2, we get the 0.14, which is, if you were to change it on your calculator, oops, that's still 1/7. 3 over 21, 1/7. 2 over 14, 1/7. So what it's saying is if you have bigger waves, which kind of makes sense, they're going to be further apart. As these have a distance from crest to crest of 28. The height is, say, I didn't write on here if it's feet or whatever, but 4-foot waves. If they're 14 apart, so if they're a little closer, then the waves are smaller. So smaller waves are closer and the bigger waves are farther apart. Kind of makes sense. Okay, so we would say what would be our equation for the direct variation? Y equals 1/7 x. 1/7 is our constant of variation. Okay. Let me give you same information, just a little bit different way. This is how some of the problems are in the book. So example, it says here, y varies directly with x. So what they're saying is that's direct variation. In other words, you want to think, what's the equation again for direct variation? Y equals kx. So it says when y equals 20, when x equals 8. So if you just think of it just like our table. So how would you figure out the constant of proportionality? 20 divided by 8, so 20 divided by 8 gives you 2.5. So we would say y equals 2.5x. And then it says, find the constant of variation, proportionality, and write an equation relating x and y. So that we did. Okay. Step 2 is find the value of y when x is 6. So in other words, if x is 6, we want to find y. So how would we get that? Just times it by 2.5. Good, so we get 15. Okay. So that's how you do that. I believe, yes. Okay. Now, the other thing I wanted to show you guys is from 2.5. And let me just bring that up on another one here. I'll just show you this real quick. One of the things that we're going to talk about quite a bit in Algebra 2 is taking a look at, you'll do it maybe more in science, where you collect some data. In other words, take a bunch of temperatures or take a bunch of times, time something, collect some data, and what we're going to do quite a bit in Algebra 2 is we want to model. We want to find an equation to fit that data so that we have a mathematical model for it. Okay? For example, I had used the example the other day of like the temperature outside. So let's say, I'm just going to throw some points up here just to pretend. Let's say as the day goes on, so let's say I put my x-axis as the time and the y-axis as the temperature. In general, what's going to happen as we go further into the day? I mean, if you start early in the morning, in general, it usually rises. So in other words, let's say at 6 o'clock this morning, I took a temperature. At 7 o'clock this morning, I took a temperature. At 10 o'clock, I take another temperature. And then we get a bunch of readings from all over. Okay, I check you can check the other weather stations or whatever and get some data. Okay? You can kind of see, we could model that pretty closely with a linear function, right? It pretty much follows a straight line. I mean, it's not that you're not going to find all the points on a perfectly straight line, but they're pretty much following a line. They're just kind of going up. It's getting warmer as the day gets later. When they're going up to the right, just like a positive slope, we call that a positive correlation. Okay. Now, what would be something that would maybe go down over time? Maybe if you do the temperatures in the evening, say if you started like, I don't know, 8 o'clock, then you take 8 p.m., 9 p.m., 10 p.m., it's going to keep getting a little cooler. So if we were to do like this, and say I start here at 8 p.m., and say maybe over here is like, I don't know, 2 in the morning or something, then it's going to be going down, right? It's going to be getting colder as the night goes on. So what would you guess you call that? Negative correlation, yes. So just think negative slope, negative correlation. Okay. Now what we're going to do here, I'm going to show you how you can do this with Excel. You can put in some data and have it do what we call the line of best fit. What's basically a line of best fit? If you can, what we're going to do is we're going to use Excel. I'll show you here in a minute. And then I have part of your homework is your 2.4 book work. And the other part of your homework is you're going to use Excel in the lab to do some lines of best fit, to do some linear regression, we call it. So what you do is we would use Excel to calculate, I only wanted to draw one, but the line that kind of fits the pattern for that. Okay? What's something you could use? That's a line of best fit or a line of linear regression. How could that be helpful, or what might you use that for, that line of best fit? Yes, that's probably the main thing. I could predict then, okay, say I took my last reading here at 1 in the afternoon. Maybe I want to make a prediction. I want to make it like see what the trend is, so that by 3 o'clock in the afternoon, I want to be able to predict, okay, at 3 o'clock, if it continues this current linear function, what should the temperature be? Use it for predictions. Good, Brad. So let me show you on Excel here real quick, and then we'll go down to the lab, and I'll give you some time to do that. So let me give you your sheet, because I've got the instructions all on here. And what I'll do is I'll just hand out a bunch and then just bring back up the extras, just to make it a little quicker. I'm going to type it over here. Okay, guys. If you could just put on the overhead here any extras. Now I put the directions up at the top here. You enter your data. So in other words, I just as a quick example, I put in here, okay, the hours after 5 a.m. So this would be 6 a.m., 7 a.m., 4 hours later, 9 a.m. I just threw up just a bunch of numbers. And here are the temperatures I observed, okay? So you enter your data. It says insert scatter. So in other words, if you look up here, we're going to go to our insert menu. We've got insert scatter. And we're going to do the one with only markers. So that's this one, okay? And let's see. Oh, let me get rid of this here for a minute. Let's see. Yeah. How can I get rid of this thing here? Okay. let me just do this. There we go. Okay. Looks like I'll have to add in there that you need to highlight your data, highlight your table. I'll have to add that on there. I missed that. So shows my data. Okay. Select the chart area. So I select my chart. I go up here to Layout. Okay. And then it says Analysis. So I want to go, it's right here. Trendline. They just call it a trend line here, linear trend line. Okay. So there's my line of best fit. If I right-click on my trend line, it'll give me Format Trend Line. And click the box to display the equation. So that's down here at the bottom, display equation on chart. So here you guys, it gave me the slope and the y-intercept for this line of best fit. So you could use that, like Brad said, to make a prediction. Say I want to just predict, okay, 6 hours after 5 a.m., what am I predicting if it follows this linear function, what my temperature is going to be? So there's just 3 of them on here that for your homework to do. When you do, just take note, you guys, when you do your predictions, I want you to use this equation. I want you to plug it in, and that'll give you your most accurate prediction. I don't want you to just look at the line and just guess, oh, it's about 42 degrees. I want you to figure it out. So you're going to do 2 things for your homework. This sheet we'll hand in tomorrow, and then your 2.4 book work. Okay? So we can head down there. Grab the same seats as before.